Section 16.2, Part 2 in Stewart's textbook, and which is the same as 16.2 in Thomas's textbook. This is line integral over vector field. So remember in previous section we talked about line integral over a scalar field, scalar function. Here we're going to take the line integral, perform the line integral over a vector field. Remember what the vector field was. It's a function in R2. It's a vector whose components are functions of x and y. Some books, they use p and q. In R3 is a vector whose components are functions of three variables, namely m and n and p. Some books, they use p, q, and r, but it's just a matter of choice of variable they use. Remember, one of the special vectors was gradient vector. Vector field was gradient vector, which was a vector field in R2 or R3 whose components were partial derivatives of the what? Scalar function. Remember, f is not a vector field, it's a what? Scalar function. It has a range of real numbers, whereas a vector field, the range is what? A vector, but the domain could be what? All set of order pairs in R2 or all set of order triples in R3. The notation is nabla, which is pronounced del. So that's what this notation upside down triangle is, which means gradient. And basically, it describes the direction and rate of the fastest increase of f, the gradient. I think we have talked about this in previous chapters. So if you can find a vector field, which happens to be the gradient of a scalar function, in many applications, f represents a potential energy, and the gradient of the vector field indicates the corresponding force. If there exists a scalar function such that the vector field is gradient of that function, then the field is called conservative. And f, the scalar function f, is called potential function. So if there exists, that means we must find it, because sometimes not all the vector fields are what? Conservative. Some are not. Example of conservative vector field would be gravitational as a conservative. Non-conservative would be like friction. So if you can find a scalar function such that its gradient is the same as what? The vector field itself, then the vector field is called conservative field, and what? The scalar function is called potential function. The word conservative comes from principle of conservation of energy. So that's like if you roll an object, okay, from top to bottom of the hill, and the sum of the potential function and kinetic function at point A is exactly the same as at point B, then we say there has been a conservation of energy, therefore we have a what? Conservative what? Vector field. So I'm going to do three applications. The first one is work. Work is defined as force times displacement. Remember, the amount of work is in the direction of the what? Motion. So it has to be what? It has to be so-called horizontal component of the force times displacement. So the horizontal component of the force is what? Magnitude of the force times cosine of theta times the magnitude of the unit tangent times arc length. So this would be like force times displacement. So the displacement is the arc length. Do you see it? And this is the force. But that's exactly the same as what? F dot t ds. So F is in the direction of the motion. So remember, the definition of the work is what? Force times displacement. But I'm only interested in the horizontal component of the force, which is in the direction of the unit tangent. So if I take what? F dot t multiplied by displacement, which is ds, and by the way, that's arc length, then what I have found is the amount of energy which takes what? Let's say to move an object or a particle on a curve from one point to the next. Okay, so therefore what we have to do is in the problem we have to express the vector field in terms of what? Parametric equation of the curve. And then this is the definition of what? Unit tangent. And this is the definition of what? This is what arc length is equal to. Remember, arc length was the square root of dx dt squared plus dy dt squared dt. But this guy is just derivative, the magnitude of the derivative of the what? Of the parametric equation of the curve. In other words, if this guy, r prime was velocity, so we're talking about speed now. So this would be like the same as speed times dt. So anyways, the bottom line is the work is F, what? In terms of the parametric equation, dotted with r prime dt. Notice these guys cancel. And all you are left with is dr dt, which is the same as r prime, and you still have your dt. And t goes from, let's say, a to b. Let's say here, I can say t goes from a to b, and then I get a number, and that would be how you evaluate the work of moving an object on a curve from one point to the next point on that curve. So let's do an example. Let's say find the work done by F in moving the particle along the curve. This is like the helix, where t goes from 0 to 2 pi, and the vector field is defined as 2y comma 3x comma x plus y. Or you could say 2yi plus 3xj plus x plus yk. In other words, you can also express the vector field in terms of the, write it as linear combination of these standard what? Unit vectors in positive x and y and z axis. Remember, this was the formula. The work is equal to what? And the line integral over the vector field. In this scenario, the vector field is the amount of force, but it's just the horizontal component of the force. And then this would be like displacement. So that would be F, what? Expressed in terms of parametric equation, dotted with, that's a dot product, r prime, what? T dt. So what you do, you take the derivative of your curve. So remember, the curve is helix. So you take its derivative with respect to t. Express what? The vector field in terms of the parameter. Remember, x is equal to cosine of t, y is equal to sine of t, z is equal to what? T. So express these guys in terms of parameter t, and that's how the vector field is going to look like. Now take the dot product of this guy and this guy, evaluate the integral with respect to t, and notice t goes from 0 to 2 pi as the problem stated. And notice the order matters. So at the end of the day, you get pi units of work. Okay, so that will be the amount of energy which requires what? To move an object on a helix from 0 to what? 2 pi, provided here is the vector field, which is the force field. Speaking of the units, if the force is in newtons and displacement is in meters, the work is in joules. If the force is in pounds and what displacement is in feet, then you have, or foot, then you have foot pound. So those are the units. Okay. The next example is called the flow of a fluid along a curve in space. So this is about the flow of a fluid, okay, along a curve in space. The flow along a curve from A to B, okay, is given by the same integral which we use to find the amount of work moving an object, on a curve done by this force. So it turns out the same integral is also called flow integral. If the curve is closed, then A the initial and the terminal point what coincides, and the flow will be called circulation around the curve C. So in other words, if the curve is closed, okay, so the initial point matches the what? Coincides with the terminal point of the curve, then the flow integral will be called circulation, and that's what this notation in what? On integral sign is. That just means what? The curve is closed. So this indicates you are doing this integral, line integral, over a closed curve. Okay, so the question is, a fluid velocity field is given by this vector field. So this is the velocity field. Instead of force, now I'm defining this as if it was the velocity of the fluid. Find the flow along the what? Along the helix, which is cosine sine t over 6. And believe it or not, I get the same answer I got for finding the work. But now this would be what? The units of flow. All right, speaking of circulation, circulation in a layman's term is amount of pushing force along a path. So a vector field is usually the source of the circulation, and the more circulation, the more pushing force you have. Suppose we do an example. The example is, suppose a fluid velocity field is given by this. Find the flow of the fluid along the path curve, and the path is x is equal to y squared. So one more example of the what? Flow integral. Remember, the question is find the flow of the fluid along the curve. Okay, so you go flow is equal to what? Line integral over the vector field times displacement, which is, we know it's f dot dr. So what you do, you immediately what? Parameterize this parabola. I parameterize it as let y be equal to t, x is t squared, and t goes from what? 2 to -1, because notice the direction of the what? Curve. And because t was the same as y, so I have to what? Take the values of the y. So y goes from 2 to -1. Notice the direction is super important in this type of integrals. So keep track of the direction. Note the order here. Do you see it? So what I did, so the parametric equation of that parabola is t squared comma t. So I need the derivative. So that's 2t1. I take that and dot it with this vector field, which is the fluid's velocity. But remember, I have to parameterize this. So I'm going to replace the x with what? T squared. And I'm going to replace the y with what? T, because I'm supposed to express this in terms of parametric equation of the curve. When I do, I get this. Now I have to take the dot product, f dot dr. And then notice t goes from what? 2 to -1. 2 to -1, not the other way around. Be careful, because y was exactly the same as t. So I have to follow the order of the what? Values of the y. When I do, I get -39 over 2. So the question is, what is the significance of having a negative flow? The significance of negative flow is the fluid is flowing what? Opposite direction of the curve. Okay. Now let's do a circulation problem. So here is the velocity vector field. Here's the curve, which is what? A circle. Center at what? 0, 0, radius 1, and t goes from, let's see now, 0 to 2 pi. So these are all given. The question is find the circulation of f around the circle. So you have the parametric equation of the circle, and t goes from 0 to 2 pi. Circulation is what? The same as what? Flow integral, except the curve is closed, so that's what this notation is for, but everything is pretty much the same. So what you do is parameterize this guy in terms of the parametric equation, replace the x with cosine t, y with sine t, and then take the derivative of this guy. Remember, r is equal to what? Cosine t comma sine t. So you need r prime first, which is negative sine t cosine t. And that's what this guy is. Don't forget the dt, and t goes from what? 0 to 2 pi according to the problem. Okay, so t goes from 0 to 2 pi. So when I take the dot product, I come up with 0 because these guys pretty much cancel. So all I'm doing is just taking the integral of 0, which is 0. So what's the significance of 0? That means there was no circulation. So the flow was not rotating. And if you would graph this using technology or plotting points, this is how, what is it? The vector field looks like. It doesn't look like it's circulating. Okay, so it doesn't look like the field is rotating. As a matter of fact, later on, we will see, oh my goodness, 0, 0 is called a source because notice the vector field are dissipating from the what? 0. They're going away. They are diverging. So we call 0, 0 as a what? A source. So there are three cases when you do circulation. If the circulation comes up positive, we have a counterclockwise rotation. If it is negative, we have a clockwise rotation. If it is 0, there is no circulation, just like our problem. Notice there is no circulation, otherwise I would what? Get a type of vector field which would circulate or rotate. Okay, finally, we talk about something called flux. That's F-L-U-X. This is the notation. It comes from a Latin word for flow. However, the flux is across a curve or a surface, is the amount of fluid that crosses what? The curve or surface in a flow unit time at any what? One point. So it's the amount of fluid which crosses a curve or a surface per unit time, like, so many gallons per minute. However, the formula for flux is what? Closed is a line integral over vector field, okay, dotted with the normal vector ds. So this is called flux of F across C. So N is the outward what? Outward pointing normal vectors on curve C. So they have to be pointing out, and those are the normal vectors. Remember, the flow is going across the curve. It doesn't go in the direction of the motion. It goes across the curve. Because of that, so we need what? A normal component of the force, not tangential. Remember, the flow integral was about what? Line integral of what? Of tangential component of the vector field. In flux, you have to take the normal component of the vector field. So that's why we need to take the normal outward pointing normal vector to the curve in order to find what is known as flux, which is the amount of fluid crossing the vector or surface, later on we'll do surface, per unit time. As I mentioned, like so many gallons per minute. So the line integral with respect to arc length of f dot n, scalar component of f in the direction of outward normal n. So question is, where does this, so how does this apply to a specific formula or specific vector field? Well, the bottom line is flux measures how much matter, like let's say water, crosses C in unit what? Time. As I mentioned, like so many gallons per minute. If the vector field is mn, so remember this is the same as m is a function of xy, so is n. As a matter of fact, some books they might call it p and q. That's not important. And the other factor we got to keep in mind is c traces what? counterclockwise exactly once. So in other words, I can have what? Clockwise or counterclockwise. In both cases, n happens to be what? In clockwise situation, n is defined as k times t. Remember what k was equal to? K was the unit vector 0, 0, 1 along the what? Positive what? Z-axis. If the motion is what? Counterclockwise, the n becomes t cross k. Okay, in both cases, k is the unit vector along the what? Z-axis. So I'm taking the what? Clockwise case. So the what? The normal has to point out. So in this case, what I have to do is take the cross product of k and t in order to get a normal which points out of the curve, not into the curve, but out of the curve. Keep in mind k was 0, 0, 1. Unit tangent was what? Dx ds, dy ds. Now I have to take the cross product to find the normal vector. So this is the what? Normal vector to what? Normal vector to curve C, correct? Which is t cross what? K. So do the what? Cross product. You will end up with dy dx comma minus dx ds. Remember, ds was arc length, correct? Okay. So f is what? M and n. So I take the what? Dot product of f and n, and this is what I get. Remember, I have to multiply this by ds. The ds is canceled. And lo and behold, I have the formula for flux, which is what? Line integral equals mdy minus ndx. So this is the formula we use to find the flux, what? Over a closed curve, which is the amount of matter which crosses curve C per unit time. Thank you.